Bonnet theorem. Now, statement of the theorem is prove that dw bar by ds plus tau, which is equal to capital W, where small w bar, which is a normal angle, and capital W, which is a torsion of the geodesic, which is a torsion of the geodesics. Now, our aim is to prove this differential equation of first order. Now, if P is some point on a curve, then we know that this is a unit tangent vector and this is a principal normal vector and it is a binormal vector. And normal to the surface, capital N, which makes angle W bar with the principal normal vector n cap. Then it means dot product of capital N and small n, which is equal to cos of omega, cos of W bar, and dot product of this and B vector, which is binormal, is equal to sine of W bar. At point P, so we already discussed this for dot product is equal to cos of W bar and this dot product is the sine of W bar. Now since from the second equation, since B dot in geodesics, so B dot capital N cap, which is equal to sine omega. Now differentiate this equation with respect to S. If we differentiate this equation with respect to S, then first differentiate this B dash dot capital N and B into capital N dash vector, which is equal to derivative of this through S. So this is cos W bar and dW bar by ds, these values. Now by Freenet formula, this B dash, which is equal to minus tau n. So remember this dot n cap plus this B, because T, N and B are orthogonal system, then T cross N, which is equal to B vector. So B vector, which is equal to T cross N vector, dot N dash vector, and which is equal to cos W bar into W bar by ds. That is same as in these equations. Now this value is equal to cos W bar dW bar over ds, which is equal to minus tau, this small n vector into capital N, plus this is scalar triple product, which is T small n and capital N. So this can be written as n dash, then T, then small n. So n dash, T and small n. Now torsion of the geodesic W, which is given by, that is already we discussed in the previous lectures, that is equal to W n cap, which is equal to n cap dash cross R dash. So this value, because R dash is equal to T, unit tangent vector, so this value is equal to n capital N dash cross T vector, right? Now substitute this value in this equation, so that we will. So first, if you have any doubt of torsion of geodesic, then go to the previous lecture, then see the definition of torsion of geodesic, that is denoted by W. So remember that is denoted by W. Now from this equation, cos W bar dW by ds, so that is the same, right? So minus tau, this values, now substitute this value, this is cos of W bar, this is cos of W bar, right? So minus tau cos W bar. Now from this equation, so what is this? This is a this cross product T dot product n vector, right? So we write here, this is n cap dash cross T dot n vector. Now what is the value of this that is in this equation? This is capital W into capital N. So these are the vectors. So here we write capital W and dot product of capital N and small n, right? Now this is equal to minus tau cos omega cos W bar plus by definition that is in the first equation capital N dot small n, that is capital N dot small n, which is cos W bar. So this is equal to cos W bar, right? So this value is equal to cos W bar dW bar by ds equal to minus tau cos W bar plus W into cos of small w bar. Now this is a non-zero. So we divide by cos W bar, then we get dW bar ds, which is equal to minus tau plus capital W. So this can be written in this form. So that is a differential equation that is very important, and this is called a Bonnet theorem. So this is Bonnet theorem. In the examination, it was asked that state and prove Bonnet theorem. So you must know the statement of this theorem, right? Now, after that, the next theorem, the statement of next theorem is, this is again very important result. If a curve on a surface satisfies two of the following condition, then remaining condition is also satisfied. So we have three condition. Condition number one, curve is a line of curvature. Condition number two, curve is a plane curve, right? If curve is a line of curvature, then it means it is a geodesic curvature is equal to 0, right? If curve is a plane curve, remember that. So that will not given in the theorem, right? So you should know that if the curve is a line of curvature, in that case capital W, which is equal to 0, and if the curve is a plane curve, then tau, which is equal to 0. And third property is the normal angle of the curve is a constant. Normal angle means small w bar, right? So basically it is the application of Bonnet theorem. So that we discussed here, that will be used in these theorems. Now the given statement is, if two part are given, any two part A, C, B, C, ja, B, A, then the third part is also true. Now from this, first we take A and B is given, right? So in mathematically, in the first part, and we want to prove C, right? So in the mathematically, capital W 0, small tau 0. So this is a Bonnet theorem. So this 0, this 0. So what we get? We get dW bar by ds equal to 0. So W bar equal to constant. So what is W bar? It is a normal angle. It is a normal angle. The normal angle of the curve is constant. So it proves the first part. Now in the second part, A and C is given. Now it means A and C is given, mean W is equal to 0, right? C means W bar, small w bar is constant. It means its derivative is 0. So these two terms are 0. If these two terms are 0, then it implies this equation, this is 0, this is 0. Then tau is equal to 0. That is our aim. That is our aim. If this 0 and this 0, then tau is 0, right? Then part B is satisfied, right? So part B is satisfied. Now given part is B and C, right? So what do you mean by B in mathematical? B means tau is equal to 0, and C mean W bar equal to constant, small w bar. So B mean tau equal to 0. C mean dw bar by ds equal to 0. Right? So by Bonnet theorem, this equation is satisfied. In this equation, this term is 0 and this term is 0, then it means capital W is 0. So it means the property A is satisfied, which means curve is a line of curvature. Now, after that, this is a proof of this theorem. Basically, in this theorem, we only used the Bonnet theorem, and Bonnet theorem contains three parts. So if two are zero, then third will be zero. So basically, that is the idea behind this theorems. Now, after that, we will prove this result, that is very important. Prove that kappa square, which is equal to kappa g square plus kappa n square, where kappa denote curvature, kappa g geodesic curvature, kappa n normal curvature. So that result we already proved in the previous article. So see that result. Now next is very important result. So that we will prove in the next lectures.